So welcome you all in my next lecture. So now this lecture I will talk about again the kind of continuous functions from several variables, that means of continuity of f from Rn to Rm. In my last lecture I already introduced the notion of continuous functions from Rn to Rm, and I have kind of provided few examples, and then I said some kind of that if I have a functions from R2 to R, then I have defined two functions small g and small h, and then I said that continuity of f will not guarantee the continuity of small g and small h, and similarly continuity of small g and small h will not guarantee the continuity of small f. So these are the few things I have discussed. So now this time I will discuss little more about continuous functions, that means some more examples, and I will say that okay, given a functions capital F, you have some component functions, and is there any relations between the component functions and the original functions. Okay, so let me start with that. Okay, so now if you remember that in my last lecture I talked about algebra of continuous functions. So that means if I have two continuous functions, then if I take the addition, this is also continuous functions. If I hit it by scalar, this is also continuous functions. If my function is continuous at some point, that function is also continuous at that point. Then if I have two functions f and g, if they continuous at x naught, then inner product between f and g, this is scalar valued functions, this is also a continuous functions. If I take the norm, that is also a continuous function, and of course quotient, whenever it makes sense, that is also continuous functions. Once I have that algebra, within that from that kind of algebra of continuous functions, you can prove examples of various continuous functions. For example, that's why I have written this application theorem of my previous slides. If you look my previous slides, I have listed out the algebra of continuous functions. Using that one, you can easily check that if I take a function p, which is a function from R2 to R, so this sort of function is also a continuous functions. So this is p of xy, this is ax square plus b of xy plus ua square plus dx plus uy plus f. This is a second degree polynomial. Okay, so where a b c d e f are real constant. Now examine the continuity of this quadratic polynomial in two variables in R2, and you can easily check. Why? Because it is nothing but the, you can do that. Okay, so each component, if you say this is a continuous function, then sum is a continuous function. In my last class I discussed, right? So that only fact you have to use that ax square is a continuous function, but yes, it's a polynomial of second degree 2 or interpolynomial degree n. It's a nice function, it's a continuous function. So therefore sum of continuous function is also a continuous. This is one of the way. Of course you can use the epsilon delta definitions and to prove that one. Okay. Also these are the exercise you should do, that examine the continuity of kth degree polynomial in two variables. Okay. So here earlier one is only second degree, now you can have the kth degree polynomial, then you can use the algebra of continuous function, you will be able to prove that. Similarly kth degree polynomial in n variables, that is much more complicated, you have too many terms will be there, because n variable means you have x1, x2, xn, and then kth degree, that means all possible combinations will be there. Even then, just using the algebra of continuous functions, just prove very what is called simple functions, the continuity, and then do the algebra of continuous function, then you will be able to prove that. Rational functions in n variables, quotients of two polynomials of n variables, so that means the rational function, that's also you can talk about the continuity using the whatever the algebra of continuous function I have listed out using that properties. Also you can talk about examine the continuity of this. This also you can either use the algebra or just use the epsilon delta definitions, that also, because you have a sine function, cosine functions, you just estimate the continuity of capital F at any point. So you can use that kind of trigonometric formula, and using the epsilon delta definitions, then I think you will be able to prove the continuity of capital F. Okay, so now this is another kind of characterizations of the existence of continuity of capital F, like for the limit existence of limit, you know, that is called sequential criteria. Sequential criteria for the existence of limit, I think you people are familiar with. I already discussed in my kind of last slides that of existence, suppose if I have a functions from Rn to Rm, and suppose take a limit point x naught, and if I say that okay, the limit of capital F at the point x naught, say L, capital L, if and only if any sequence xn converges to that limit point x naught, the corresponding sequence f of xn should converges to L. So this is if and only, this is called sequential criteria. Similar sort of theorem you can have it in the context of continuity. So let capital F is a functions from Rn to Rm, take a point x star is in D, the following two statements are equivalent. What are this? Capital F is continuous at the point x star, and for each sequence xk in D whenever it converges to x star, the sequence f of x should converges to f of x star. Okay. So this is the kind of sequential criteria for the existence of continuity. Okay. Now I think I should say that the importance of this theorem, if I want to prove that the function is continuous, it is better to use epsilon delta definitions or some kind of algebra of continuous function. But this theorem is useful to prove that a function is not continuous, that means negative way. That means if I want to show that my function's capital F is not continuous, then as I told you in the limit case, that means take two sequences converges to the same point, but the corresponding image sequences f of x and f of y and converges to two different limits. So that means in that way you can say that the function is not continuous. So that means to prove that function is not continuous, sequential criteria for continuity, I think that is much more useful rather than proving the continuity. You can prove it, I am not saying you cannot prove it, you can prove it, but rather to prove that function is not continuous sometimes is much more useful. Okay. Okay. So using this theorem you can prove, for example, okay, I already that this is the using that theorem you have to prove that it is continuous. Okay, you can do that, not an issue. So what is that function? G of xy is equal to x square y divided by x4 plus y square. If xy is non-zero and g 0 0 is equal to 0, then you can use that g is a continuous function on R2, but it is not continuous at the point. So that means I am taking origin from R2. On that set one can prove that it is a continuous function. Again you can use any sequences. Okay, take some point, prove any sequences, and somehow you justify your argument that both the sequences g of xn converges to the same value g of xy. So okay, you can check it, you can prove this using the above theorem, the continuity of g. Okay, so this is another important theorem. Using that theorem also you will be able to prove you will be able to prove many continuous functions. If I show that, okay, check whether this function is continuous or not, using that theorem also you will be able to prove it. What is that theorem? This is called compositions of two continuous functions is a continuous function. That means I can take two continuous functions, capital F and capital G. Whenever the composition makes sense, can I say that that function is also continuous at that point? Okay, that's how the theorem is. So start with the functions capital F from say D subset of Rn to Rm. Now I am starting with the function g from f of d. Look, so I need to start with g from f of d, otherwise the composition does not make any sense. So starting with the function g from fd, which is subset of Rm to Rk, then I can make sense the composition function capital H. What is that function? So H acting on x, which is nothing but g of fx. Now f maps any point x to f of x, and what is f of d? That means this is the range of f. So that means f of x belongs to range of f, which is nothing but f of d. So therefore g makes sense. So therefore g of f, g acting on f of x makes sense. So therefore h makes sense, and this is called the composition functions. Now the question is, now what I am saying is that we start with a point x naught belongs to d, then write y naught is equal to f of x naught. Then what is my statement? It says that if capital F is continuous at x naught and capital G is continuous at y naught, then the composition functions, which is nothing but h, which is g composed f, that's how I have written, one can write it's also continuous at the point x naught. So that means if I take two functions capital F and capital G, if I consider the function g composed capital F, whenever it makes sense, then if capital F is continuous at x naught and capital G is continuous at y naught, which is nothing but f of x naught, then I can talk about the continuity, or I can say that capital H, the composition functions, also continuous at the point x naught, because composition functions is a function, so h is a function from where to where? H is a function from D subset of Rn to Rk. If f is a map from D subset of Rn to Rm, G is a map from Rn to Rk. So G H function, that means G composed F, is a map from D subset of Rn to Rk. Okay, so using that theorem, so this is, that means if I have two functions, whenever composition makes sense, and if the functions are continuous functions, then the composition function is continuous. Using that theorem, I can say that these functions f of xy, which is sine of xy, is also a continuous function. Why? Okay, I can define two functions. I can show that this is nothing but a composition of two nice functions or two continuous functions, and therefore this function is a continuous function. Okay, so define say f1 functions. Okay, so f1 function, say I am defining say from R2 to say R. So f1 of say xy, which is nothing but xy, product functions, and define f2. This is my f1. Define f2 from say R to R. What functions? f2 of say x is equal to sin x. Okay. So, now f1 functions, this is I am just value of f1 at xy, which is product of x or x times y, and this is a polynomial in xy. These are continuous functions. f2 is a sine function, this is a continuous functions. Now I can write my f, which is nothing but, what is this? I can write this is f2 composed with f1. So, f1 if I acting on xy, what will happen? This is f2 of f1 xy, okay, and f1 of xy I know this is f2 of x times y, and f2 function means what? This is sine of xy, and that is exactly the functions. So, therefore, I can write my small f into f2 composed f1. f1 is a function which is very nice function R2 to R, which is nothing but x comma y goes to x times y. This is a continuous function. You can just use the epsilon delta definitions or sequential criteria, whatever it is, you can prove that this function is a very nice function, is a continuous function. Similarly, f2 functions is a from R to R function, is a sine function. This is also a continuous function. Composition of two functions follows from this theorem, and therefore, this function is continuous. So, that is the way you can check that if someone say that okay, check whether this function is continuous function or not, you can use that kind of theorem. So, that means to check the continuity, plenty of ways you can check, either use the epsilon delta definitions, or use sequential criteria, or use algebra of continuous functions, or composition of two continuous function is continuous. So, various way you can check the continuity of functions from Rn to Rm. This is another important theorem. So, as I said that given a functions f from Rn to Rm, you have m many component functions, and already in the case of limit I said or I discussed that the existence of limit of capital F, if and only if existence of the limit of the component function. Similar sort of things also true in the context of continuous functions. That means, if I start with the functions capital F from Rn to Rm, it will have m component, that means small f1, small f2, small fm, each of them functions from D subset of Rn to R, real valued functions. Now, if I take a point x naught is in D, then f is continuous at x naught if and only if each of the component function is continuous at x naught for each I between 1 up to m. Okay. So, that is very nice actually. So, later on I will discuss some examples, then we will see if I have a, if I just say that okay, check the continuity of these functions. You just look at the component functions and somehow try to conclude that okay, look, these are the component functions, these are very nice functions, they are continuous functions, and therefore, the original functions capital F is continuous. So, that is very nice. So, let us see some examples. So, this is a very powerful theorem. So, again to talk about or to check the continuity of some several variable functions, one can use very much this theorem. Okay. So, example applications of my last theorem. So, what is that? So, define a function say f from R to R3. What sort of functions? So, since it is taking values in R3, it will have expect 3 components. What are the components? So, this is the definition of my functions. So, again just if I have a functions from Rn to Rm, you know how to kind of write the component functions by taking the corresponding inner product with the E1, E2, E3 or up to Em. So, that is how you can immediately kind of conclude that what are the component functions. So, my first component function is f1 t is equal to 2t, second component function is f2 t is equal to sin t, third component function is f3t is equal to t plus 1 by t square plus 1. So, each of the functions from R to R real valued functions, these are the continuous component functions of the functions capital F, but these are very nice function component functions. This is a continuous function, sine function is a continuous function, this is cosine of two continuous functions are continuous functions. So, therefore, I have all the component functions of capital F are continuous, and therefore, by my earlier theorem, my functions capital F is a continuous functions. So, therefore, by using the theorem mentioned my earlier slides, I can talk about the continuity of capital F on R. So, that is another very nice. So, kind of using the continuity of the component functions, I can talk about the continuity of capital F. Okay. So, this is another example. So, this is the functions from R2 to R3. So, that means it will have 3 components. You guys identify the component functions. So, first component function xy divided by x square plus y square. Second one is sin x. Third one is x plus 1 divided by y square plus 1 whenever xy belongs to R2. Of course, these functions make sense only if I take out the point R2 minus 0, 0, otherwise this does not make any sense. So, therefore, I think I should say that this G is defined for all xy R2 minus 0, 0. Okay. I think it should not be R2, it should be R2 minus 0, 0, because otherwise it does not make any sense. Okay. And this function is a continuous function, because this is a very nice function, second component function, sine function is a continuous function. third component function, that is also cosines of two polynomials like x plus 1 divided by y square plus 1, and it is never vanishing. So therefore this is also continuous functions. Only the problem is the first component function. There you might find some difficulties, though at the point 0 0, but I take out the point 0 0. So therefore it is a very nice function. Again, it is a cosines of polynomials in x and y. So this is also continuous functions. So it will create the difficulties only at the point 0 0, but I am defining the function g on R2 minus 0 0. So therefore this functions is actually continuous function on R2 minus 0 0. Okay. So I think I should write here R2 minus 0. Okay. So now some other characterization I should say, as I said that I have defined the concept of compact sets or connected sets. Now I have the notion of continuous function. So is there any interplay between that? So before that, let's see, this is very nice actually. That's what I have written. It is additional information or other characterizations of continuity. In some other books you can see those sort of definitions of continuous function. So what I am doing, so I am starting with a functions capital F, which is from D subset of Rn to Rm. What I am taking, I am considering a set E, which is subset of Rn. Then I am defining a set. What is that set? F inverse, capital F inverse of E. Please remember, this is not the inverse of the function. This is called inverse image. That means this is just a notation. It is a set. What sort of set? I am defining that it is the set of all points in the domain such that whenever capital F acting on X, it should be an element in E. So that means I am starting with a set E subset of Rn. I am defining a set capital F inverse of E, which is called inverse image of that set. That means it is the set of all those points in the domain. Whenever capital F acting on X, it should be an element in E. That's how this is called inverse image. Once I have that kind of notion of this set, then the following statements are equivalent. What is this? First of all, capital F is continuous function. If capital F is continuous from D subset of Rn to Rm, then whenever, if I take any O in, I think there is a little mistake. Yeah, this should be Rm. This is not N. This should be Rm. That means I have a functions from where? Rn to Rm. So I am considering a set E in the range or in the codomain. Then I am trying to define a set in the domain. That means this is F inverse E, which is the collection of all those x such that Fx. So this is a subset of D. So given a set in the codomain, I am defining a set in the domain, which is nothing but the inverse image, and that I have defined. Once I have that one, then the following things are equivalent. Given if capital F is continuous functions on D, if O is any open set in the codomain Rm, then there exists a open set O star in Rn such that your inverse image F inverse of O is nothing but O star intersection D. That means it's actually, so one can say that this is also open in D. That means what it says, if I have a continuous functions from D subset of Rn to Rm, if I take a open set, so if I take a open set, so that means if I have a function F from D subset of Rn to Rm, if I take a open set here, so this is open, say U open set, then if I take the inverse image in D, it is also open in D. So that means the inverse image of open set is also open if my capital F is continuous function. That is it. So that's why I've written the inverse image of every open set is open. That is very nice. Similarly, if I have any closed set in the codomain, then there exists a closed set. One can give the existence of another closed set in Rn such that the inverse image of my closed set, which is nothing but K star intersection D. So one can say that this is also closed in D. In other words, inverse image of closed set is also closed. So in some books you can see this is also definitions of a continuous functions. In fact, if I have a topological space, that is the way one can define a function is continuous from some one topological space to another topological space if inverse image of open set is open. So this is one of the, so I have defined the definition of continuity in terms of epsilon delta, but one can prove that if I have definition of continuity in this way, so these are the following theorem is also true. That means if I take an open set in the codomain, in inverse image is also open. If I take a closed set in the codomain, its inverse is also closed. Okay, so now the interplay between continuous functions and connected set. So I'm starting with the functions capital F from D subset of Rn to Rm. Now, if I take any set S is S subset of D, this is called the image of f at x, which is nothing but the value of f at x where x is running over S. That is the image of S under the map F, I can say, or capital F acting on S, or I will say that image of S under the map capital F. What is my theorem? This is a very nice theorem. It says that if I have a continuous functions on D and if S is any connected subset of D, then the image set, that means f of S, is also connected in Rm. So that means continuous image of a connected set is connected. That's exactly. So continuous functions map connected set into a connected set. That is a kind of very nice property, that is, or I should say that is the interplay of the continuous function and connected set. That means if I have a function which is from Rn to Rm, if I have a connected set, connected subset of D, then the image is also connected. So now if I just take n is equal to m is equal to 1, that means if I have a f from I subset of R to R which is continuous on I, and suppose I is an interval which is actually a connected set, then what it says, fi is also a connected subset of R, and if I have a connected set which is consisting of more than 1 points, that means it is actually an interval. And that is sometimes known as the intermediate value property for the real valued functions of real variable. That means if I take any two distinct values in the range f a and f b, there should exist a point x such that f of x, or if I take any value, so like intermediate value property, if I take any value f a, say c less than f b, okay, so then there exists a point d naught in open in a b such that f of d naught is exactly equal to c. This intermediate value property, and this is nothing but, that means it maps interval to interval. So that I can think about as intermediate value property for real valued functions of real variable. If I take n is equal to m is equal to 1, and in the context of Rn to Rm, a continuous function map a connected set to a connected, that means image of a connected set is connected. Okay. Now what will happen for the case of compact set? Again, so if I start with the functions capital F from D subset of Rn to Rm, again this is start with a set S subset of D, this is my image set. So this is again a nice theorem. It says that if capital F is continuous on D and if S is a compact subset of D, then f of S, that means the image set, is also compact in Rn. So that means continuous functions maps compact set to compact set. So that is the interplay between continuous functions of compact sets, and earlier is the like continuous functions and connected sets. So that means if I have a function from Rn to Rm, if I take a compact set in the domain set, then the image is also compact. Okay. So in particular, if I take n is equal to m is equal to 1, so suppose f is a map from closed interval a b subset of R to R, and this is a compact set we know in R. So therefore image, it should be also compact, and we know that what are the compact subset of R. A compact subset of R are closed and bounded interval. So therefore it is of the form C to D, where C is strictly less than D. Okay, so another few properties. What is the meaning of bounded functions? Okay, first let me see. So if I have a functions capital F from Rn to Rm, so what is the definition of bounded functions? A function f is said to be bounded on the set D if there exists a positive number capital M such that norm of fx which should be dominated by capital M, and this should true for all x. So that means if the range is norm of the value of the range, that means consider a functions capital F, consider the image, that means f of x where x running over D. If the norm of fx is dominated by a fixed number, then I will say that this function is bounded functions. And immediately once I have notion of bounded functions, then this is a very nice theorem. It says that if capital F is continuous on D and if it is defined on a compact set D subset of Rn, then it is always a bounded. So just now in my earlier theorem, I have observed that it maps compact set to compact sets. So now I have a capital functions f defined from D to Rm, so defined on D to Rm, and D is compact. So therefore f of D is also compact, in Rm. Okay. But I already discussed in my earlier slides that a compact set in Rm is closed and bounded. So since f of D is compact, so therefore it is closed and bounded. So therefore the function is bounded. So therefore that's why it says continuous function on a compact set is bounded. F of D is bounded means what? F of D is bounded means norm of fx which is less than some constant k for all x in D. That's the meaning of bounded. If you know that when I talked about the definition of bounded set, a set is called bounded if I take a open ball with some center x naught and finite radius r such that I can push my set inside that ball. So that means if I have a ball of some center x naught and finite radius r, and if my set inside that, then I'll say that that set is bounded. Similarly, that's the same way, or that can be expressed in terms of norm. I'll say that a set is bounded if norm of fx is lesser or equal to some fixed constant for all x running over that set, and that exactly is going on here, because image of a compact set is compact, and compact set in Rn I know it is closed and bounded, and therefore my function f is bounded. So now once I have the bounded set, so therefore I can talk about its supremum and infimum, at least for the norms case. So I am starting with the functions f from Rn, k subset of Rn to Rm. If capital F is continuous on k and k is compact on Rn, then the theorem says that there exists a point P and Q in K such that this supremum and infimum this exists, because I just proved that image of a compact set is compact. So therefore this supremum and infimum exists. But what is more important is that I can have the existence of P and Q in the set K such that this supremum is nothing but norm of Fp and this infimum is nothing but norm of Fq. That is very important. That means it attains the supremum, attains the infimum. That means it attains the extremum. So that is the beauty. So that means that's why I have written the continuous functions norm of f. So the continuous functions, so if capital F is a continuous functions, norm of f is also a continuous functions. So that continuous function norm of f attains its extrema value on the compact set K. So that is very important. So that means supremum infimum always exists because it is bounded, but more important is that it attains at the point. So that is very important. In particular, if I take say m is equal to 1, that means I am considering the real valued functions from the n-dimensional Euclidean space. That means the functions f from k subset of Rn to R, which is real valued. A function small f is continuous on k if k is a compact set in Rn. Then there exists point P and Q in K such that value of the function at P, which is nothing but the supremum, and value of the functions at Q, which is nothing but the infimum. So in other words, what I am trying to say is that if I have a functions f from Rn to R, okay, and of course if I have a functions f defined on a compact set subset of Rn to R, and if my function f small f is continuous, then this supremum and infimum exists. As I said, continuous image of a compact set is compact, it is a compact set in R, so therefore it is closed and bounded, so therefore supremum and infimum exists. But what is most important part is that supremum and infimum attains at the points. That means there exist points P and Q in the set K such that this supremum is nothing but the value of f at P and this infimum is value of f at Q. That is more important rather than the existence but follows, because continuous image of a compact set is compact. But another important part is that it attains the supremum and infimum at some points in the domain K. Some other properties, okay, this is kind of you can say, okay, what it says is that properties of continuous functions, or suppose if a function f is there, suppose inverse exists, then what can I talk about the continuity of the inverse functions? Here is the theorem. It says that let K be a compact subset of Rn. Okay, I am starting with a compact subset of Rn. Let capital F defined on a compact set which is subset of Rn to Rm, which is a continuous as well as it is a 1-1 or injective functions. So injective functions mean that inverse exists. So this 1-1 means 1-1 functions or injective functions, that means inverse exists on the domain D. And if I define the range say K star, which is nothing but the range, that means the image set, that means capital F acting on K in Rm, then the following conclusions true. What are the conclusions? First, the inverse functions capital F inverse from K star to Rn exist. Okay, so capital F is a map from K subset of Rn to f of K. Okay, subset of Rn. So now this is 1-1. So it is injective on K or 1-1 on K. But whenever I am thinking about from K to Fk, this is also surjective. So that means it is bijective, that means inverse exists. Inverse exists from where to where? From Fk to K. So that means from Fk means I have written K star. So that is why the inverse function F inverse from K star subset of Rn to Rn exists, number 1. Number 2, F inverse is a bijective function from K star to K. So injectivity on K is given. Just in the image set you consider f of K, that means the range, which is denoted as K star. So that means it is injective and bijective from K to K star. So therefore inverse function exists, and inverse function is also bijective from K star to K. Moreover, that capital F inverse is continuous on K star. That is very important. So therefore, if I have a compact set K on Rn, if I have a function capital F defined on that compact set, if it is continuous as well as 1-1, then the inverse functions from the set K to the range of f of k, that means k star, it is exists, it is bijective, and the inverse function is also continuous function. So that is the point. So that means if I have a continuous functions on some compact set, if it is continuous and injective given, so I am starting with a continuous function, suppose oneness is given on the domain set k, then what you do from the domain set, consider the range set, that means f of k, from k to f of k, that means k star, it is a, you can think about the function is bijective, that means inverse function exists from f of k to k, and this inverse function not only bijective but also it is a continuous function. Okay. So there is a very kind of serious note is there in the above theorem. If I drop the condition k is compact, then the continuity of f inverse may fail. So that means it is bijective, that is not an issue because it is injective on k, that means inverse exists on k, and if I consider the range as f of k, that means bijective part is fine, bijective, it is bijective, then inverse exists, but I cannot talk about the continuity of f inverse. So this is a very nice example. So for example, this function capital F from closed interval 0 to 2 pi to R2. So what is this one? So this is my R and this is R2. So if you just draw a picture, it is actually a circle. Okay. So this function, so capital F, so it is a function, nice function from closed interval 0 to open 2 pi to R2. This function, this is a continuous function, right? And inverse is also exist. However, since closed interval 0 to open 2 pi, it is not a compact set because it is not closed. So it is a bounded set, but it is not a closed set, so therefore it is not a compact set. So therefore, even if f inverse exists, but one can check that capital F inverse is not continuous. In fact, it is not continuous at the point 1, 0. So therefore, compactness of the domain is very important. If we drop the conditions of the compact sets on the domain, it may fail. The conclusion may fail. Okay. So now the last one. So I can also talk about the continuity of capital F at some isolated point. So but before that, I need to explain what do I mean by isolated point. So here is the definition. So if I start with a set S subset of Rn as a non-empty set, a point x naught is in Rn is set to an isolated point. This is very important. Look at the definition very carefully. A point x naught in Rn is said to be isolated point of S if x naught should be an element in S and x naught is not a limit point of S. Now, if you remember what is the definition of limit point of S, if you remember a point, I have a point, I have a set. I will say that that point is a limit point if I take any neighborhood of x naught, right? It should contain a point of x except the point x naught. That is very important. So that means I have a set S, so I have a point x naught. I will say that it is a limit point for any neighborhood, whatever neighborhood I can take around the point x naught except the point x naught, that should exist another point from the set S. This is a limit point. So I am saying that x naught is not a limit point. That means it says that for every neighborhood should replace by there exists a neighborhood. So that means there exists a neighborhood of x naught, so that it should not contain any point of S. That means it should be negative, right? So that means limit point means whatever neighborhood I can take around the point x naught, it should contain at least one point from the S except the point x naught. I am saying that it is not a limit point. That means I should have the negation of this statement. That means instead of every neighborhood, it should be there exists a neighborhood, and instead of contain at least one point, it should not contain any point. Okay, this is that kind of things. So that means if I have a set S, if I take a point x naught, I will say that it is an isolated point if x naught is in S and x naught is not limit point. That means there should exist a neighborhood of x naught such that it should not contain any point of S. Okay, let's see some example. So for example, S subset S is equal to n set of all natural numbers in R. I am saying that for each natural number n, it is an isolated point of S. Why? Okay, so this is my R and this is say 0, 1, 2, minus 1. So sorry, minus 1. This is n. No, so 2, 3. Okay, so this is my set S. So I am saying that each number, so 0, 1, 2, these are isolated points. Why? First of all, if I take a point 1, it is an element in S. That means it is a natural number. And I am saying that there exists a neighborhood which does not contain any other point of S except the point 1. So that means if I take a neighborhood like say half neighborhood, if I take this small neighborhood, it will not contain any other natural number except the point 1. So that means it is an isolated point. So that's the definition. The definition is the limit point definition is what? So for every neighborhood of x naught should contain at least one point of S except x naught. It is not a limit point. That means there exists a neighborhood of x naught. There should not be any point on S except x naught. So that exactly, if I take a point 1 or 2, this is the neighborhood. There should not exist any other natural number except the point 2. So therefore these are the isolated points. Now consider this set S is closed interval 0, 1 union 2. So, one can easily say that this is an isolated point, and this is okay. Why? Because suppose this is 0, this is 1, and this is my 2. Now, I can take a neighborhood here. So, in this neighborhood there is no point from 0, 1 except the point 2. So, therefore, this is an isolated point. I have written two notes, this is very important. Note 1, so if x naught is an isolated point of S, that is very important, we cannot find a sequence of points from the set S converging to x naught. And in other words, also we cannot find a path in X along which the point x naught can be reached or approached. So, that means if I have a point x naught which is an isolated point of S, that means we cannot find a path inside the set S which approximate the point x naught. That is very important. Note 2, because it is isolated, you cannot have any other point on the set S except the point x naught. Note 2, so it says that the values of wave functions capital F at the isolated point will not affect the continuity of f at the isolated points. Therefore, the function capital F is always continuous at the isolated points. Note 1 says that if I want to talk about the continuity of f at some isolated points, use the sequential criteria. Think about any sequence converges to x naught, consider the image sequences, it should converges to the value f of x naught. That is the meaning of continuity, right. Now, if I take an isolated point, just note 1 says that there cannot exist, we cannot find any path or any sequence which converges to that point and that point are coming from S. So, therefore, I can say the continuity of f at x naught vacuously. Since there cannot exist any sequence I cannot find which converges to x naught, so that I can talk about the convergence of the image sequence, therefore, vacuously I can say that my function capital F is continuous at the point x naught. That exactly I have written. The values of a functions at the isolated point will not affect the continuity of it. That means vacuously it is continuous. Example, if I have a function S from closed interval 0, 1 to 2, so 2 is an isolated point. So, define, let us define f x is equal to sin x, x from 0 to 1, and define f of 2 is 100. So, then f is a continuous at 2 as well, because you cannot have any sequence from the set S which converges to 2 except the point 2, and the value of the function at 2 is defined. So, therefore, my function is continuous. Okay, so I think I should stop here. So, that is kind of concept of continuity of several variable functions from Rn to Rm. So, that means I have introduced the notions of continuous functions, provided various examples, and then I talked about that given a function small f, or I should say that given a function shape it will have a component functions, then what is the relations between continuity of the component functions and the original functions. Then I have discussed that if I have a functions from R2 to R, then I can define two functions keeping one variable fixed like gh, then is there any connections about the continuity of f and g and h. And then I talked about the interplay of the continuous functions with compact sets, with connected sets, so the various properties. So, I have discussed. So, that is kind of information about the continuity of a function from Rn to Rm. I think in my next lecture I will talk about the existence of derivatives. So, that means a major part is that I should say that the concept of sequences, limit, convergence, continuity. So, those are the concepts if you realize that with like almost similar like in the case of real valued functions of real variable with an appropriate changes. That means I just replace all those definitions and replace mod by norm, almost everything becomes kind of similar in the context of several variable. However, whenever I will talk about the differentiability of multivariable function, this is not so straightforward. There is something there which is not just parallelly, I cannot transform from the real variable case to the multivariable case. It is not possible, because you can easily guess, because in R2 or Rn there is no kind of notions of division. Since there is no notion of divisions, and if you see the definition of differentiability in the real case, there is a concept called quotients, and you have to take the limit of those quotients. So, that kind of business will not be available in the context of several variables. So, therefore, I need to see in a different way, and therefore, the notions of differentiability will be different compared to the real variable case. I think that is the part little more challenging for the differentiability. In my next lecture I will talk about that. Thank you very much.